name is James Roche. I'm an executive consultant and Aerospace and Defense Practice Director at CIMData. Today, we will be discussing a major advance in PLM technology capability and methods for dealing with two of the significant threats to a successful implementation. The digital thread has been a core element of the PLM vision for decades. The concept of linking multiple representations of a product, each tuned to the needs of various creators and consumers along the life cycle, is powerful. With recent advances in technology, solution enablement, the digital thread has become a technical possibility. In response, leaders in many industries are starting to implement multiple view bill of materials solutions and envision expanding these solutions upstream and downstream throughout the product lifecycle. While the potential benefits of automatic reconciliation and synchronization across lifecycle views are many and substantial, and the prospect of providing autonomy to manufacturing and service engineering to more quickly and efficiently resolve production problems and customer service issues is compelling, the journey is fraught with challenges. During today's webinar, we will focus on the multi-view approach for implementation of EBOM and MBOM and SBOM structures, which are core to the concept of digital thread. We will examine two major difficulties that commonly arise and prescribe methods to overcome them. We'll begin our discussion by describing the context within which multiple view bill of materials implementations are being planned and executed. This includes not only solution concepts, but also the context of benefits and risks, especially who is impacted and how. We will close with a few summary observations as guidance to those who are pursuing or plan to pursue a multi-view approach to BOM management. If you have questions, please submit your question in the Zoom question and answer feature. All questions will be answered as time allows at the end of my presentation. With a degree in physics and graduate work in materials engineering, I spent my early years in manufacturing engineering and development before transitioning into PLM. At General Motors, I served as chief architect for global engineering systems. This was followed by many years as PLM practice manager for various consulting firms, delivering strategy and solutions for several major aerospace programs, as well as other interesting clients, such as Proton Cars in Malaysia, Bose, Church & Dwight, Ethicon Endosurgery, and Medtronic Bradycardia. After a stint with Siemens DIS, I retired and then joined CIMData 9 years ago to deliver industrial consulting and help develop PLM strategy and policy from an industry perspective. Just a few words on CIMData for those of you who may not know us. CIMData was founded in 1983 as a strategic management consulting firm totally dedicated to the advancement and productive application of PLM. With the quality of staff that we have attracted to the firm and through their experience over decades, CIMData has amassed a wealth of intellectual capital. We leverage that capacity to deliver strategic advice and consulting through a comprehensive integrated set of research, education, and consulting services. Those services include research, where CIMData is a recognized authority on the PLM market and PLM technology analysis. Education, where CIMData provides PLM certificate programs, conferences, seminars, and workshops. And consulting, ranging from strategy and vision for industrial clients to solution evaluation and market planning for the solution providers. One of the unique characteristics of CIMData, in addition to being solely focused on PLM, is that we do not sell or implement PLM software or implementation services. We are technology agnostic, and when dealing with an industrial client, we are completely focused on their successful business transformation. Some of the key understandings you can expect to gain from today's session are as follows. The complexity and significant change in processes and roles required to deploy a multi-view BOM solution. These are the processes and roles that control definition of the product, how it is manufactured, and how it is serviced. How to effectively engage impacted business areas to define, refine, and validate future state multi-view BOM processes and roles. We will discuss how engagement is key to getting it right and having the solution adopted. The concept of digital thread is illustrated in various creative ways by the PLM solution providers. Several are shown here, and they all present the core theme of multiple views of product information, appropriately structured for the use of creator and consumer at various stages of the product lifecycle. In today's discussion of the multi-view approach, we will focus on the industries that pose the greatest challenge for BOM management. Industries producing complex products where quality is an existential imperative. Industries such as automotive, aerospace, shipbuilding, military vehicles, and medical devices. In these industries, BOM accuracy impacts safety and is subject to government regulation. In today's discussion, we will focus on the anchor point for the digital thread, the transition of BOM management from engineering, the EBOM, to manufacturing, the MBOM. There are currently two approaches for managing this transition. One is the single BOM approach, where product engineering creates an EBOM and then structures and augments that information in compliance with direction from manufacturing engineering. The resultant single BOM released by product engineering is in reality an MBOM. One great advantage of the single BOM is the absence of ambiguity. In the dual BOM approach, product engineering creates and releases an EBOM. Manufacturing engineering then restructures and augments the EBOM information to create and release an MBOM. With this approach, each MBOM is optimized for use and may be changed independently within the domain where it is created and consumed. The great disadvantage of this approach is the reconciliation and synchronization of the two BOMs is heavily manual and accuracy is never 100% certain. Within the last 3 to 5 years, commercial PLM solutions have advanced to enable the multi-view approach. In this approach, a consolidated information resource contains all of the information and maintains all of the relationships between data elements that are needed to support the perspectives of multiple communities, such as product, manufacturing, and service engineering. The promise of this approach is automated reconciliation and synchronization across domain views that can be created and managed with optimal autonomy. The potential benefits of automatic reconciliation and synchronization across life cycle views are many and substantial. Elimination of time and effort for reconciliation and synchronization of the BOMs, reduction of cost and quality issues due to inaccurate data, elimination of time and effort to validate data which is not trusted, and reduction in lead time and increased efficiency and quality of supplier collaboration resulting from trusted data. But what about the people who do the work of creating and managing the EBOMs, MBOMs, and SBOMs? They are the ones who must absorb the change in their way of working. And as they say, as the great poets say, and there is the rub. To answer these questions, let's spend a few minutes talking through a case study. There are many transition scenarios that we could examine. For today, we will consider the benefits and risks at the working level for an A&D company transitioning from a single BOM, which is an MBOM, to multi-view EBOM-MBOM solution. Looking first at cost reduction, we see a shift in responsibility from product engineering to manufacturing engineering for release and change of the MBOM. As might be expected with the shift, it is estimated that the effort for release and change will decrease. Interestingly, there is a significant effort by manufacturing engineering in the current state to prepare and follow up on release and change requests with product engineering, and this effort will not be required in future. In addition to cost benefits, there are schedule and quality benefits. Currently, despite the effort of manufacturing engineering to prepare and follow up on change requests to resolve plant production issues, only 70% of requested changes are ever processed, and the elapsed time is 40 days. In the future, manufacturing engineering will process 100% of these changes and within 10 versus 40 days. Benefit quantification was qualitative, but judged to be substantial. These benefits, along with others, provide a strong case for investment in the proposed transformation. On the cost side, it was not difficult to identify and quantify cost elements, lay them against a timeline for execution, and calculate a return on investment. But what about risk? There are two categories of substantial risk that are inherent in a transformation of this nature, and they are often overlooked or underestimated. Let's look at them now, and later we will discuss methodologies for managing and mitigating them. The first is organizational risk. Transitioning from current to future state will introduce a massive disruption in roles and responsibilities. Manufacturing engineering must define and staff a new role for BOM creation and release. They must also accept responsibility for accuracy and timeliness of the BOM creation and release. Product engineering and manufacturing engineering must redefine their interdependent processes and responsibilities. In product engineering, workload and responsibilities will decrease, yes, overall, but will increase in some new and sometimes unexpected ways. Will the new organizational definition work? And importantly, will it be adopted? Then there is the technical risk. Commercial PLM solutions that enable the multi-view approach to BOM management is new. Many capabilities are required. Are there gaps in these new capabilities? If the software has the capability, is it easy to use? It is worth noting that a gap to some extent is in the eye of the beholder. We'll have more to say on this later. These two categories of risk can be addressed by applying targeted methodologies within the framework of a well-structured transformation program. In order to discuss these methodologies, we must first present a transformation program organization of work. CIMData's recommended best practice for organization of work within a PLM transformation program is that design and implementation of solution elements is executed within a set of implementation streams. That coordination and integration of the implementation streams is managed within a program management stream, and the deployment of the solution elements and ongoing user support are provided within a production support stream. The figure on this slide illustrates the structure of a roadmap designed in conformance with the organizational work just described. Implementation streams operate under the guidance and control of an ongoing governance, program, office, and shared services stream. And what they produce is deployed and supported by a system go-live and production support stream. A lot of interesting activities that are important to the success of the program happen in the top stream, such as enterprise architecture and organizational change management. I'd love to spend time talking about both of these streams, but they are not central to the subject of today's discussion. Where we want to focus is on the implementation streams, what they are, how they are normally executed, and why they must be executed in different from normal ways for multi-view BOM management transformations to be successful. Each bullet in the definition of implementation stream describes an important aspect of the concept. An implementation stream is a self-contained unit that delivered change to a discrete community that transforms from their current way of working to an improved state with measurable benefit. Each stream or substream is a bounded building block of the total solution. Two implementation streams, which are relevant to today's discussion, are named. Several others are shown for illustration purposes. An implementation stream is commonly executed as a set of 8 activities, ranging from forming the stream project team, including SME representatives from the targeted business area, to deploying the completed solution stream. Activities 2, 3, and 4 address the multiple dimensions of transformational solution, data, process, and technology capability. It is noted that the methodology is amenable to agile development practices. There are 2 significant variants of the usual implementation stream activity sequence that have been crafted to address the two categories of risk described earlier. If the subject of the implementation stream requires advanced or unevaluated technology capabilities, then two substreams are added. A substream is added for technical capabilities verification prior to proceeding with solution development, and a substream is added for vision and solution architecture definition, which is the predicate for capabilities verification. These two substreams may be executed iteratively. First, a vision and solution architecture are defined based on understanding of the technology capabilities. The use cases are defined and a prototype built and tested against the use cases. If the prototype demonstrations are successful, then the project progresses to solution implementation. If not, then the vision and solution solution architecture are modified and the prototype is revised and retested. If the subject of the implementation stream is complex, especially if the solution will involve significant change to process and roles, then a substream is added for developing and exercising a value verification prototype prior to completion of a solution development, moving on to deployment. A value verification prototype is not the same as a pilot. A pilot is a final pre-production verification after a solution has been developed and tested. The value verification prototype is used to complete the development of a complex and incompletely specified solution through trial, evaluation, and refinement. At the heart of the exercise is refinement and confirmation of the solution's value. To confirm that value will be achieved when the solution is implemented in the real world, certain conditions must be satisfied, such as engaging expert SMEs from the target user community. They are the real world. Define the complete solution, including processes and roles. Include design and testing of an organizational change management plan. Identify and reach agreement on value metrics and values. Evaluate, revise, and repeat trials as many times as it takes to reach a satisfactory outcome with consensus of the SMEs from the user community. An example of how value verification prototype substream might play out is shown in this reference client example. In the current state, manufacturing engineering provides input to product engineering, and product engineering is responsible for creation, release, and change of the BOM. This is the case we showed earlier. In the first future state iteration, a new organization is set up within manufacturing engineering with a responsibility to define the BOM. This requires new skills, imposes a higher workload, higher responsibility, and higher risk on the manufacturing engineering organization. The existing team within product engineering has reduced workload and reduced responsibility and reduced risk, but there are still new responsibilities that emerge for defining what an BOM is and how it will be managed. And even with these changes, there remains an area of ambiguity between the two domains, having to do with responsibility for verification of consumption, reconciliation, change impact analysis, and change process. In a second alternative, the responsibility for creating the BOM is within a new organization, but also within that organization is responsibility for consumption verification, reconciliation, and managing change. And this new organization straddles the domains of product and manufacturing engineering. It's not imposing new responsibilities, new workload, and new risk on manufacturing engineering, but on some jointly shared organization that has the responsibility for making both domains successful. There are obvious advantages to this approach but there are also disadvantages. So it must be sorted out with the organization that's in process of making the transition, and they must decide themselves which is the approach they can commit to making work. The point of this example is not to recommend a solution, but to illustrate that multiple solutions, each with pluses and minuses, exist, need to be tested, and arguably are best tested, revised, and retested by those who will be directly involved in the real-world execution. That is not to say that the user community should be given the assignment and turned loose. They definitely should be doing this work under the guidance of experts. At this point in time, considering the maturity of technology and maturity of industry's application of the multi-view approach to EBOM, MBOM, SBOM management, it can be argued that both technical capabilities verification and value verification prototype are appropriate methods to include in a BOM management transformation program plan. In summary, with recent advances in PLM solutions, the multi-view approach for implementing the digital thread has now become technically possible. Starting with the anchor point for the digital thread, which is the EBOM, MBOM, and SBOM, is a sound strategy, and one that is beginning to be pursued aggressively within industry. The complexity of required change to processes and roles and the newness of the technology present two categories of substantial and often unrecognized risk. But fortunately, there are novel methodologies which have been crafted to effectively address these categories of risk and protect the benefits inherent in the multi-view approach to BOM management. If you are interested in more information on this topic, I suggest that you tap into the excellent work being done by a team of aerospace and defense industry experts who've been engaged on this subject intensely for the past 4 years. They released a position paper in January 2019, which you will find of interest. This paper is posted on the Aerospace and Defense PLM Action Group website. This team will be reporting on a multi-view BOM solution evaluation benchmark, which has recently been completed. The report out is expected by the end of May. I apologize that we ran over due to technical problems. I am available if you would like to participate for a few more minutes, and I could take some questions. If you have questions, just write them down in the QA function of the Zoom application, and I'll be happy to get to them. We have a couple questions up. The first one is, you gave us an A&D case study. Would the same apply to other industries? I would say the answer is yes. It really depends on the complexity of the industry. The idea of the multi-view BOM approach has been around for a while, and there's been capability within PLM technology solutions for a while. And that capability has been sufficient in industries that have products of lesser complexity than, say, airplanes and tanks and ships and whatnot. And in those industries, the need for reconciliation and assurance of consumption between EBOM and MBOM is not so severe. And but in all industries, to implement a change in the approach, which gets right at the core of how the product definition is managed and the manufacturing process definition is managed and how those two are synchronized. It's really very fundamental to the business. So I would say yes, depending on the industry, the technology challenges or lack of familiarity or maturity of the technology may not be so severe as it is within aerospace, but certainly the disruption to the way of working is very substantial. And the idea of doing value verification prototype would certainly apply and be useful. Second question, there are a lot of capabilities mentioned on the technology risk slide. Are there gaps in those capabilities? So I mentioned gaps earlier in the presentation as being somewhat in the eye of the beholder. So what constitutes a gap? The technology has a certain capability. That's a reality. That's fundamental. Individual within the solution provider company who tells you what that capability is and how the solution will operate is giving you a certain representation of the fact of what the solution can really do. And then if you're an industrial user, you have an expectation. And so as you hear someone tell you what the solution will do, again, there's a level of interpretation. So there are many steps in the process between the reality of what the system does and what the industrial user expects it to do that could constitute a gap. And I would say at this point, the capability of the technology to actually meet the requirements have been demonstrated, but the understanding of exactly what those capabilities are, how they operate, how to exploit them, there's definitely a gap there. So the technical capabilities verification is really a reconciliation between user expectations and what the technology actually can deliver. And where the gap is, whether it's actually missing capability in the technology or just a misunderstanding and need for adjustment of expectation on the part of the user, that's a point of philosophical debate. But I would say that the capabilities of the actual technology as it's delivered and what it can do are capable of addressing and adequately performing as needed to manage multiple views within a common structure. The third question, what about the as maintained BOM? It's an excellent question. The multi-view BOM approach would support any of a number of different product structure views. So it could be extended to include as maintained, although you get into issues of how do you collect that data and is it stored in multiple places if it's acquired through some type of a service, a customized service management system, then there needs to be an integration and mastering of that information within a single PLM application so that you have that single consolidated data structure that you can draw the different views against. Well, we've gone over time by 10 minutes. Again, I apologize for the technical difficulties. I think it's a good time to draw the session to a close. If any of you would like to continue the conversation, please reach out. And to all of you who participated today, I want to thank you for your time and your attention. Goodbye.